A year ago, Nvidia's own CEO stood in front of investors and said quantum computers were 15 to 30 years away from mattering. $8 billion in market value vanished within hours. Quantum stocks collapsed. The message seemed final. Then, quietly, without the fanfare of a product launch or a flashy keynote, Nvidia did something that contradicts everything Jensen Huang said that day. They built a bridge, a real one, running through microseconds instead of miles, connecting the most powerful classical chips ever manufactured directly to quantum processors built by 17 different companies. Read that again. The man who dismissed quantum computing as decades away just spent a year quietly wiring it directly into his own machines. To understand why this matters, you first need to understand the problem that has haunted quantum computing since the very first working qubit flickered to life in a laboratory. Qubits are extraordinarily fragile. Unlike the ones and zeros inside your laptop, which sit stable and predictable for years, a qubit can lose its quantum state from something as small as a stray photon brushing past it, or a whisper of heat leaking through a supposedly perfect vacuum chamber. According to Nvidia's own technical documentation, these units of information are delicate and error-prone, requiring complex calibration, quantum error correction, and other control algorithms just to keep functioning correctly. And here's the part that almost nobody outside the field understood until recently. Those correction algorithms cannot run on the quantum computer itself. They have to run somewhere else, on conventional hardware, and they have to run fast enough to catch and fix errors before the fragile quantum state collapses entirely. What most people are not seeing is that this single requirement, moving data back and forth between quantum and classical systems faster than the human eye could ever perceive, has been the quiet, unglamorous bottleneck standing between quantum computing's laboratory promises and its real-world usefulness. For years, every major quantum computing company solved this problem their own way, building custom, proprietary connections between their specific quantum hardware and whatever classical computing they had access to. There was no shared standard, no common language. Imagine if every internet provider on Earth had built its own private, incompatible version of the internet, unable to talk to any other networks. That was quantum computing's dirty secret for the better part of 2 decades. Different companies, different hardware, different control systems, all racing toward the same goal but speaking entirely different technical languages, with no unified way to plug any of it into the kind of raw computational horsepower that only companies like Nvidia could provide at scale. This is not chaos. This is strategy, or at least it was about to become one, because on October 28th, 2025, at Nvidia's GTC event in Washington, D.C., that fragmentation problem got an answer nobody entirely expected. Nvidia announced something called NVQ Link. On the surface, it sounds like just another piece of corporate networking jargon, the kind of announcement that gets a polite round of applause and is forgotten by lunchtime. But underneath that unassuming name sits what Jensen Huang himself described in unmistakably dramatic terms. In the near future, Huang said, every NVIDIA GPU scientific supercomputer will be hybrid, tightly coupled with quantum processors to expand what is possible with computing. And then came the line that should stop you in your tracks. NVQ Link is the Rosetta Stone connecting quantum and classical supercomputers, uniting them into a single, coherent system that marks the onset of the quantum GPU computing era. Think about what that phrase actually implies. A Rosetta Stone doesn't just translate one message, it unlocks an entire lost language permanently for everyone who comes after. Huang wasn't describing a product update. He was describing the moment 2 separate branches of computing history stopped evolving apart from each other and started evolving together. This wasn't just Nvidia talking to itself either. United States Secretary of Energy Chris Wright weighed in on the announcement with language that elevated this from a corporate product launch into something resembling a matter of national strategic importance. Maintaining America's leadership in high-performance computing requires us to build the bridge to the next era of computing, Wright said, accelerated quantum supercomputing. He went on to describe NVQ Link as providing the critical technology to unite world-class GPU supercomputers with emerging quantum processors, creating the powerful systems we need to solve the grand scientific challenges of our time. When a sitting cabinet secretary starts describing a corporate interconnect standard using the language usually reserved for space programs or nuclear energy policy, that tells you something about how seriously the people inside the room actually took this. This is where it gets worse for anyone still clinging to the idea that quantum computing is a distant next-decade curiosity. The government treating this launch as a matter of national competitiveness is not a coincidence. It is a signal. So who actually showed up for this? Not 1 or 2 companies testing the waters, but 17 separate quantum hardware builders committing to the same architecture on day 1. Alice and Bob, Anion Computing, Atom Computing, Dirac, Inflection, IonQ, IQM Quantum Computers, Orca Computing, Oxford Quantum Circuits, Pascal, Quandela, Quantinum, Quantum Circuits Incorporated, Quantum Machines, Quantum Motion, Quera, Rigetti, CQC, and Silicon Quantum Computing. Read that list again slowly, because what makes it remarkable isn't just the number, it's the diversity. These companies build quantum computers using completely different physical approaches. Some use superconducting circuits cooled to near absolute zero. Some trap individual ions with electromagnetic fields. Some use neutral atoms held in place by lasers. Some use photons of light itself as the carrier of quantum information. In almost every other technology race in history, competing hardware approaches fight it out for years before one wins and the others fade away. Here, nearly every major approach in the entire field agreed, simultaneously, to plug into the same interconnect. Alongside them stood 5 companies that build the specialized control systems quantum computers depend on to actually operate. Keysight Technologies, Quantum Machines, Q-Blocks, QBC, and Zurich Instruments, along with 9 of America's most prestigious national laboratories, including Brookhaven, Fermilab, Lawrence Berkeley. National Laboratory: Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest National Laboratory, and Sandia. Now, here's the honest concession. The kind any serious technical story has to make before it earns your trust for the bigger claims that follow. NVQ Link is not quantum computing itself. It doesn't make any single quantum processor more powerful. It doesn't add qubits to anyone's machine. What it does, and this is the part that actually matters, is solve the plumbing problem that was quietly preventing every one of those 17 companies from reaching their machine's true potential. Because a quantum computer without a fast enough classical partner sitting beside it is like a race car engine bolted into a chassis with no transmission. All that power and nowhere fast enough for it to go. To understand exactly how NVQ Link solves that plumbing problem, you need to understand what happens inside a quantum computer during a single calculation, because the timescales involved here are almost impossible for a human mind to intuitively grasp. According to Nvidia's technical documentation, the connection between the quantum processor and the classical computing system correcting its errors operates through what's called a real-time interconnect, a low-latency, high-bandwidth network engineered specifically to run within the operating time domain of the quantum hardware itself. In practice, this is built using a method called RDMA over Ethernet, paired with an open-source component running inside the quantum controller, all working together with Nvidia's CUDA-Q software runtime to exchange compiled data across this connection at a latency of under 4 microseconds. Sit with that number for a second. 4 microseconds is roughly 1/250,000th of a second. In the time it takes you to blink, this connection could complete that round trip, somewhere in the neighborhood of 100,000 times. That is the speed threshold required, just to keep a fragile qubit's error rate from spiraling out of control before a calculation finishes. To the programmers actually building software for these systems, Nvidia introduced an entirely new concept to make sense of this hybrid architecture, something they call the logical QPU. Instead of thinking of a quantum processor as a separate, isolated machine that occasionally hands off data to a classical computer, developers can now treat the combination of CPUs, GPUs, and quantum processing units as a single, unified type of computing device, all targetable through the same programming model built on Nvidia's existing QDA framework. Think about what that actually means for the thousands of software engineers who already know how to write CUDA code for Nvidia GPUs. Overnight, that same base of knowledge becomes a foundation for building quantum applications too, dramatically lowering the barrier to entry for an entire generation of developers who would otherwise have needed years of specialized quantum physics training just to write a single line of useful code. The numbers behind the system, once it moved from announcement to actual working demonstrations, are where the stories stop sounding theoretical and start sounding like something genuinely happening right now. At the SC25 Supercomputing Conference in November of 2025, barely 3 weeks after the initial announcement, Nvidia revealed that Quantinuum's Helios quantum processor had used NVQ Link to achieve what was described as the world's first real-time use of a scalable decoder for an important and difficult category of quantum error correcting codes known as QLDPC codes. The specific decoder implementation achieved a reaction time of 67 microseconds. Helios's own hardware requirement demanded a response within 2 milliseconds. 67 microseconds against a 2 millisecond deadline means the system wasn't just meeting the requirement, it was exceeding it by 32 times over. This is not chaos. This is precision engineering. Solving a problem that had genuinely stumped the field for years, demonstrated on real hardware, not in a simulation, not in a research paper's theoretical projections, but running on an actual quantum computer processing actual quantum information in real time. By the time Nvidia's GTC 2026 conference arrived in March, the system had moved from carefully staged demonstration to genuine public infrastructure. Nvidia released a new application programming interface called CUDAC Realtime, folded directly into the broader Q-Day Q0.14 software release, giving any developer, not just Nvidia's hand-picked launch partners, the tools to write code that sends data back and forth between quantum controllers and GPUs at that same microsecond level latency. This is the moment NVQ Link stopped being a demonstration project confined to a handful of showcase partnerships and became something an ordinary quantum computing researcher anywhere in the world could actually start building on. And the hardware ecosystem responded almost immediately. Dell validated 4 of its own server models, the XE745, the XE9680, the R77 from 5, and the R770, as what Nvidia calls real-time host platforms, successfully reproducing those same sub-4 microsecond latencies on commercially available off-the-shelf equipment. Think about what that means for accessibility. This isn't some exotic, one-of-a-kind laboratory setup requiring custom-built hardware nobody outside a handful of billion-dollar research institutions could ever hope to acquire. This is infrastructure that any well-funded university lab or corporate research division can now purchase directly from Dell's catalog. The performance benchmarks that emerge from this rollout deserve their own moment because these are not vague marketing claims. They are specific, measurable, independently reproducible numbers. Nvidia's Q-Day QQEC software library accelerates a leading error correction decoding method called belief propagation ordered statistics decoding, delivering a 29 to 35 times speedup over industry standard decoders for a single processing shot, and an additional speedup reaching as high as 42 times for high throughput scenarios where many error patterns need decoding simultaneously. The French quantum computing company Alice and Bob, working with a specialized error correction method they call elevator codes, designed specifically for the unique noise patterns in their particular style of qubit, benchmarked a 9.25 times speedup over traditional CPU-based decoding techniques, tested across 100,000 simulated computational shots running on an Nvidia GH200 chip. QC Terrell, a company specializing in quantum control software, reported that integrating NVQ Link produced a 50 times reduction in classical computing overhead alongside a 5 times speedup in overall wall clock time, meaning tasks that used to take substantially longer to complete now finish in a fraction of that time, freeing up quantum hardware to spend more of its limited, expensive operating time actually computing rather than waiting on classical systems to catch up. In April of 2026, barely a month after the public rollout began, Nvidia pushed the software further with the release of CUDA QQEEC version 0.6, which shipped with 2 entirely new real-time decoder pipelines built directly into the CUDAC real-time framework. The first, called Relay BP, is a belief propagation decoder specifically optimized for QLDPC codes, the same difficult error correction family that Quantinuum's Helios system had already demonstrated live. The second pairs an NVIDIA-designed convolutional neural network purpose-built for a technique called Ising pre-decoding, with a global decoder known as pi matching, targeting a different and equally important error correction approach called the surface code. Here's why this detail matters more than it might sound at first. These 2 code families, QLDPC and surface codes, represent 2 of the most important and widely used strategies the entire quantum computing field is racing to perfect. Right now, the same families of codes referenced in our previous research into IBM's roadmap toward fault tolerance and the University of Chicago linked research into radically reducing the physical qubit overhead those codes require. By shipping GPU-accelerated real-time decoding for both families simultaneously, NVIDIA effectively made itself compatible with almost every serious error correction strategy currently being pursued across the entire industry, regardless of which specific company or hardware approach ultimately proves most successful. This is where the story widens out from pure technical achievement into something with genuinely global human-scale stakes, because the applications researchers are already testing on this hybrid architecture are not abstract computer science exercises. They are aimed directly at some of the most consequential scientific challenges of our time. Consider the collaboration between University College London, a company called QMatter, the Technical University of Munich, Ludwig Maximilian University of Munich, and Germany's Leibniz Supercomputing Center, working alongside quantum hardware company IQM. Together, this international team demonstrated a hybrid biomolecular simulation of a G-protein coupled receptor, one of the single most important classes of proteins in all of modern medicine, responsible for how roughly a third of all currently approved pharmaceutical drugs interact with the human body. The quantum portion of that simulation ran on a 54-qubit IQM system called EuroQ-Exa, working in direct partnership with Nvidia H100 GPUs, hosted at Germany's Bayern KI Artificial Intelligence Cluster. This is not a distant speculative headline about what quantum computing might someday accomplish in medicine. This is a working demonstration, happening right now, of exactly the kind of drug discovery relevant simulation that pharmaceutical researchers have been waiting decades for classical computers alone to become powerful enough to handle, and classical computers alone were never going to get there. Elsewhere in this rapidly expanding ecosystem, Inflection announced a partnership to deploy a full NVQ Link-enabled quantum supercomputing system at the Illinois Quantum and Microelectronics Park, integrating their proprietary scale quantum computers directly with Nvidia's GPU-accelerated infrastructure to build what the company describes as a unified architecture for real-time hybrid quantum classical computing. According to Inflection's own public filings, this collaboration is explicitly targeted at unlocking new possibilities across materials, science, clean energy development, secure communications, and artificial intelligence, while directly addressing the scalability challenges that have limited quantum computing's real-world usefulness for years. Meanwhile, at Lawrence Berkeley National Laboratory, researchers achieved the first-ever integration of an open-source quantum control system called QBEC with Nvidia's DGX Spark hardware, with concrete plans underway to run AI-enhanced quantum control experiments, including automated readout classification and precision gate tuning, tasks that used to require painstaking manual calibration by highly specialized physicists, now increasingly handed off to machine learning systems running on the same accelerated infrastructure. Pacific Northwest National Laboratory took a slightly different but equally important approach, developing an open-source integration between an FPGA-based quantum control board called QUIC and Nvidia's GH200 Grace Hopper superchip, explicitly designed to lower the barrier of entry for scientists and engineers who want to explore the fine details of quantum control and measurement far beyond what typical cloud-based quantum computing services currently allow. According to PNNL computer scientist Sam Stein, the project's lead, this collaboration employs NVQ Link specifically to leverage high-performance classical GPU processors that can meet the demanding real-time computational requirements of quantum processors, and the entire system is being built as an open-source resource, meant to be shared, extended, and improved by researchers well beyond PNNL's own walls. Think about the significance of that choice. Rather than hoarding this capability behind proprietary walls, some of the most important research institutions building on top of NVQ Link are deliberately choosing to open source their work, accelerating the pace at which the rest of the field can catch up and contribute. The broader software ecosystem tells a similar story of rapid, near-simultaneous adoption. The cloud computing company Scaleway now supports Q2Q software directly from its quantum-as-a-service platform, offering execution across hardware built by Alpine Quantum Technologies. PsiQuantum, one of the most ambitious and well-funded quantum computing companies in the world, integrated Q2Q with its own simulation tool, a PsiQuantum construct, specifically to model large-scale, fault-tolerant hybrid applications before the physical hardware to run them at full scale even exists. The Technology Innovation Institute integrated its own open-source quantum software framework called Chibo with Q2Q for hybrid workload validation, with explicit plans to bring NVQ Link itself into future work. And the French company Pascal, which builds quantum computers using neutral atoms trapped by laser light, the same underlying hardware approach connected to some of the most exciting error correction research happening anywhere in the field right now, has integrated its systems with Q2Q as well. Layer all of these individual partnerships on top of each other, and what emerges is not a single company's product launch. It's the sudden, rapid crystallization of an entire industry standard happening in real time across companies that would ordinarily be fierce competitors, all agreeing that this particular piece of shared infrastructure was too important and too foundational to build separately. Now, it would be dishonest to tell this story without confronting directly why Nvidia is doing any of this in the first place, because the company's own recent history on this exact topic is more complicated and, frankly, more interesting than the triumphant framing of a corporate press release usually allows. Barely a year before NVQ Link existed, Jensen Huang himself stood in front of financial analysts at CES 2025 and delivered a starkly different message about quantum computing's timeline. Asked directly about when quantum computers might become genuinely useful, Huang said that 15 years would probably be on the early side, that 30 years would probably be on the late side, and that if you picked 20 years, a whole lot of people in the room would probably believe him. The market reaction was immediate and brutal. Shares in Rigetti Computing, D-Wave Quantum, Quantum Computing Incorporated, and IonQ all plunged more than 40% in a single trading day, wiping out more than $8 billion in combined market value within hours of Huang's comments becoming public. D-Wave's own CEO, Alan Baritz, publicly called Huang dead wrong, pointing to real, paying commercial customers already using his company's quantum systems today, not 15 or 20 or 30 years, into an uncertain future. 2 months later, at NVIDIA's own first-ever Quantum Day event in March of 2025, Huang attempted something almost unheard of in corporate history. He stood in front of executives from a dozen different quantum computing companies and openly admitted his earlier comments had been wrong, telling the assembled crowd, "This is the first event in history where a company's CEO invites all of the guests to explain why he was wrong." He drew a direct parallel to Nvidia's own early history, noting it had taken his own company more than 20 years to build out the software and hardware ecosystem that eventually made accelerated computing indispensable to the entire technology industry. And he admitted with striking candor that he had once believed a completely different computing paradigm, GPUs themselves, was going to replace computers, only to discover, in his own words, "It turned out I was wrong." Despite this attempted course correction, quantum stocks tumbled again that same day, with D-Wave falling 18%. Suggesting the market wasn't fully convinced by the walkback. Here's where it gets worse for anyone trying to paint Nvidia as either a pure believer or a pure skeptic on quantum computing. Nvidia has clearly benefited financially from quantum computing research being conducted through classical simulators, running on precisely the kind of powerful GPUs the company already sells, giving Nvidia a genuine financial incentive to keep quantum computing perpetually promising. NVQ Link, viewed through that lens, looks less like a simple change of heart and more like an extraordinarily well-calculated strategic maneuver. If quantum computing eventually does mature into something genuinely transformative, capable of solving problems no classical computer could ever touch, Nvidia has already made itself the indispensable connective tissue sitting between every major hardware approach and the classical computing power that quantum processors will always need, no matter how advanced quantum hardware itself eventually becomes. And if quantum computing continues advancing slowly, incrementally over the coming decade, rather than arriving in some sudden dramatic breakthrough, Nvidia still profits enormously in the meantime, because every single one of those 17 quantum hardware companies now needs Nvidia's GPUs, Nvidia's Q-to-Q software, and Nvidia's NVQ Link architecture just to run their existing systems at anything resembling their true potential. This is a bet engineered to pay off, regardless of which future actually arrives. Think about what that kind of structural positioning actually means for a company already sitting at the absolute center of the artificial intelligence boom. Nvidia isn't just betting on artificial intelligence anymore. It isn't just betting on quantum computing either. It has positioned itself as the toll booth, standing at the only bridge connecting both futures to each other, collecting revenue, no matter which direction the traffic ultimately flows. It's worth pausing here to acknowledge a serious and entirely legitimate counterpoint, because no honest telling of this story can pretend NVQ Link represents a universal, uncontested industry consensus. IBM, one of the most credible and technically respected companies in the entire quantum computing field, is conspicuously absent from Nvidia's list of 17 launch partners. IBM has been developing its own independent FPGA-based approach to real-time quantum error correction, entirely separate from Nvidia's architecture. According to Reuters, IBM's Vice President of Quantum, Jay Gambetta, stated that IBM's FPGA-based implementation performs 10 times faster than what's actually required for live error correction, calling the result a big deal for real-world practical quantum computing. This matters because it means the quantum computing industry has not settled on a single unified technical standard, and probably won't for years to come. NVQ Link represents the dominant, broadest coalition currently forming around this problem, backed by an extraordinary breadth of hardware diversity and national laboratory support. But IBM's continued independence is a genuine signal that at least one of the field's most credible players believes a different technical path may ultimately prove superior. This is the honest concession this story needs before its final act. Nothing here is settled science. This is a live, ongoing competition between competing visions for how the quantum computing industry's foundational infrastructure should actually be built. And Nvidia currently holds the largest, most diverse coalition, but not the entire field. So what does all of this actually mean for the near future, the part of the story where all these individual threads finally converge into something you can actually picture happening in the real world? Picture a hospital research lab 5 years from now, running a hybrid simulation of a new cancer drug candidate, where the quantum processor handles the impossibly complex molecular interactions that would take a classical supercomputer centuries to model accurately, while sitting beside it, connected through an interconnect running at speeds measured in single-digit microseconds. A bank of Nvidia GPUs continuously corrects that quantum processor's errors in real time, catching and fixing mistakes faster than the fragile quantum state could ever collapse on its own. Picture a materials science lab designing next-generation batteries or room-temperature superconductors, running simulations that were mathematically intractable for classical computers alone, but which become newly possible the moment a quantum processor and a GPU supercomputer can talk to each other fast enough to work as a single, unified system rather than two separate machines awkwardly passing data back and forth. This is not a distant speculative science fiction scenario anymore. According to the research already underway at UCL, the Technical University of Munich, and IQM, an early version of exactly this kind of hybrid biomolecular simulation is already running today on real hardware, producing real results. And this is precisely why the framing in this story's title carries genuine weight rather than empty hyperbole. Nothing will be the same, not because quantum computers suddenly became 1,000,000 times more powerful overnight, and not because classical GPUs are somehow becoming obsolete. Nothing will be the same because the wall that used to separate these two entirely different computing paradigms, quantum and classical, has been quietly, methodically dismantled over the span of roughly 5 months, from an October announcement to a March public rollout, backed by 17 competing hardware companies, 5 specialized controller manufacturers, 9 of America's most prestigious national laboratories, a sitting cabinet secretary's public endorsement, and a rapidly expanding wave of independently verified, reproducible performance benchmarks showing genuine, measurable order of magnitude improvements in how fast these two worlds can now communicate with each other. The bottleneck that had quietly stalled quantum computing's progress toward real-world usefulness for the better part of 2 decades didn't get solved by building a bigger, more powerful quantum computer. It got solved by finally, deliberately building the bridge that let quantum computers borrow the raw, brute force computational power that classical computing had already spent decades perfecting. What happens next depends entirely on how quickly the rest of this ecosystem matures around the foundation NVQ Link has now put in place. IBM's continued independence reminds us this race is far from over, and the honest, sober assessment from serious quantum physicists remains that fully fault-tolerant, broadly useful quantum computers are still years away, not months. But the specific, narrow problem this story has been about all along, the plumbing problem, the speed of communication problem, the question of whether classical and quantum computers could ever talk to each other fast enough to matter, that problem now has a real, working, independently verified answer, running on actual hardware, inside actual national laboratories, supporting actual drug discovery research happening in Germany and the United Kingdom right now. The last time a similarly foundational piece of infrastructure quietly reshaped an entire industry's trajectory, it was called CUDA, and it took Nvidia the better part of 2 decades to fully cash in on the bet. NVQ Link might take considerably less time, precisely because this time, Nvidia isn't building the foundation alone. It built it with 17 companies who all independently decided they couldn't afford not to be standing on it. If you want to understand what happens the moment one of these hybrid quantum classical systems produces its first genuinely world-changing scientific discovery, whether that's a new drug, a new material, or something nobody has even thought to look for yet, that is exactly the story we're tracking next on this channel, so make sure you're subscribed before that moment arrives. Because based on the pace of everything you just watched unfold over the past several months, it may be closer than anyone outside these research labs currently expects. Before you go, I want to know what you think this actually means for the future of computing. Do you believe hybrid quantum classical systems like this one represent the real, practical path forward for quantum computing? Or do you think a fully independent, standalone quantum computer is still the ultimate destination this entire industry is racing toward? Leave your answer in the comments below, and as always, I read every single one.